Good afternoon. My name is Ran, and this is a video of my short lecture on static friction. And this is for you, the research committee in San Luis Obispo, Cal Poly. Starting now. Our class is a General Physics 1 class, calculus based, and of course the class is empty really because it's the end of the semester right here, and we're gonna talk about static friction today. I'm starting every class with an outline of what's gonna happen in the following week. So there we go, ladies and gentlemen. Today we'll talk about friction. On Tuesday we're going to have a review session at 7 in the evening, and on Wednesday we're gonna have a context switch problem, which is one of those things that I told you about from Kenneth Heller in the University of Minnesota, where the problem is done in teams and it's as close as we possibly can get it to a real life situation. Tuesday and Thursday we'll have a lab on friction. Hopefully we'll reinforce what we're doing here today. And on Friday, set exam 1, our exam 1 of 3. Any questions? David? Now I'm sorry, as we said before, you cannot bring an iPad, an iPod, an iPhone to be used as a calculator or a friend, okay? No, seriously, we're learning skills here. These skills are, believe it or not, the easiest way of learning some problem-solving skills for engineers. Okay? So you're gonna do it in a very simple way, and then you're gonna get it right here. Then you can go to engineering, then you can get all the apps and so on, and you will understand those apps. That's the whole idea, okay? All right, let's get going. We learned about Newton forces. We learned about the importance of vectors in our presentation of nature, and how we add them up, subtract them, and so forth. And we so far encountered 3 forces. Gravity, the force with which Earth is pulling on you guys, right? The normal force, which is counteracting force, without which you would accelerate towards the center of the Earth. And of course, tension, right? And today we're gonna add up the force of friction, and we're gonna follow the same exact route as usual. First of all, we observe, which means we play a little bit. Then we are a bit more careful by measuring what's going on, using our thinking tools like drawing, using it for communication, doing free body diagrams, and only then we analyze and we figure out ratios and natural laws. Okay? So let's start. I have here 3 examples. Okay? One example here is an example where we have a track, which is metal and wood. Then here, track, metal, and wood. All right, okay? Then right here I have a clamp, and I could do the same exact thing, metal, whoops, and wood. And the reason I'm adding this one, which looks almost like it's the same exact thing, is because I don't want you to think that these contact forces are only limited to reaction to gravity. Right? In this particular case, there is a push this way, and the metal is applying its force that way. It's not related to gravity. Okay? So we have a few questions here. First one is, what happens, I don't care about gravity and normal force anymore, we've done that. What happens if I push right here? I'm pushing. No, you're not, doctor. Yes, I am, and I can prove it. Remember this little puppy? Okay, this little puppy right here is a measurement device that measures forces. Okay, you pull it, the computer reads a force in newtons. You push it, computer reads a force in newtons. So I can push it, computer will measure force in newtons. Push, 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 bigger, 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 bigger force. Whoops! At some point it moves. Okay, but not right away. As I increase the force, first, it doesn't move, doesn't do anything and then it moves. Which means, let's put our thinking caps. Is there a force at all when I start pushing, except for my push, normal, and gravity? Yes, there is. Otherwise, what would happen? When the net force is not zero, what happens? It would accelerate. Yeah. Okay? So, we know there is the metal, the wood, and then maybe my hand pushing this way, right? And I can draw a free body diagram where I take the wood and put all the forces on the wood, right? So there is gravity, normal, and I shrink it to a point. I can have a force acting that way. That's the push. And there has to be, we said, a force right there, our mystery force, which we will call F for friction rather than mystery, because we know what it will be. And of course, it kind of grows and grows until at some point it doesn't grow anymore, so the push grows bigger and the net force will accelerate it. Okay? I'm going to claim that it's actually growing and growing and growing, and then it's going to kind of break something, and then something happens. Okay? Now, is it going to be the same whether I have wood here and metal, or oiled wood and metal, or wet wood and metal? Of course not. Here's demo 1. I'm lifting this. Nothing moves, then it moves. I'll do the same exact thing with some ice, if I have any left. No, I don't. If I did it with ice, I wouldn't need to lift it as much. Okay? So in principle, by how much I lift it, if I have the same exact mass, right? By how much I lift it will kind of tell me this force of friction. What is the force of friction in all those cases? Now, I'm going to look for a second here at what this force of friction really is. So looking at the microscopic level, if this is the wood, very close, and this is the metal, actually more organized, we have here an atom of wood and an atom of metal, and this was actually conducted in a lab in 2008, a brilliant experiment where they looked at the force, and the force between an atom and a surface was measured with an atomic force microscope. And so one atom has quite a force on it because it doesn't want to move against all those atoms in a surface. But what if I apply a force right here? What do I do to all those other atoms? I get them closer and closer and closer to the surface, right? So the more atoms are near the surface, the more friction there is. Therefore, if I'm looking at the friction and the normal force, they're proportional to each other, okay? They're proportional to each other. The bigger the normal force, the bigger the friction, okay? Now we're going to use that in figuring out a device to actually, use it backwards, measure that proportionality constant. What I'll do is I'll use this demonstration. I'll say, hey, this is easy. I've done that before. If we have normal force this way, gravity this way, I know the mass, right? I know mg. I could kind of find the normal force. Find the normal force. Let's see if we can see what happens with the proportionality constant right there. So, we have here again wood, metal. This is theta. We do a free body diagram. Normal force. Gravity. Sorry, small g. And if you recall, when we did slanted coordinates, because of the slanted track, this was x, this was y, so you could say that you could break gravity into two components, Fgy and Fgx. Now if there was no friction, this Fgx, which also points this way, would cause a net force that would accelerate the object down the incline. But because we have the force of friction right there, it doesn't. So now we can look at the x component and the y component right there. I'll have to put this down so that it's not in the way. X component, if you recall, of the vector right there is going to be Fg. This is not theta, this is 90 minus theta. Cosine of 90 minus theta is sine theta, so Fg sine theta is what we have that way. Minus F of friction equals 0. And the y component is basically going to be F normal minus Fg cosine theta, right? The other component, that way. And that's equals 0. Now, if I'll call the proportionality constant, this is F friction, and rather than proportionality, I'll have a number here. It's called the coefficient of friction, and we're using the Greek letter, we call it mu, but actually I had a Greek student and he told me that this is actually me. It's not mu, it's me, right? Mu, and the subscript S is for static friction. We'll get to the kinetic friction the second half, right? And now the question that I have for you is, in a galaxy far, far away, mu s wood on metal is equal to 0.4. I would like you to find theta, okay? So, as usual, take the whiteboards. I'd like you to find what theta is. The answer should be 21.8 degrees. And I'll start roaming around the class to make sure that you're doing that correctly. That concludes my class on static friction. The rest is exercise, then kinetic friction.